to give the first talk this morning. And so Alf is going to tell us about sensitivity analysis and quantification of uncertainty.
Yeah. Thank you very much, and good morning, everybody. This is joint work together with Jens Lang from the Technical University in Darmstadt, and I will speak about sort of two, respectively three mathematical techniques which can be used to gain additional information about the models you have. And so where do we start? Assume with lowercase u, that is the quantity of interest, that's what you're interested in, and you can obtain this from a model M of a certain process which is not really of relevance here. And that quantity of interest u, that will depend on the parameters which you put into the model. And the parameters are denoted by pi. There can be more than one. And we can write this in short. U is a function m of the parameters. And the pi's, they are scalars from given ranges, for instance. There might also be functions from given spaces, like space-dependent, time-dependent functions. We'll come to that later in the presentation. And your model M, that may involve solving ODEs, solving PDEs, computing integrals, and so on. So U might not just be the solution of an ODE system, but it might be a derived quantity from that solution, for instance. So what can parameters be? Parameters, that can be material properties of the materials which you have in your process. There can be initial and boundary conditions which sort of define your process. There can be, for instance, the form, the functional type of source and forcing functions. Sometimes, you can choose one forcing function or another, so you don't know. It can be domain shape. You might have that as a parameter in your problem. Yep.
Does that also apply to measured data? Or is this more like I have something to compute?
Well, we're talking about models. There are two things. You can analyze the model. I come to that in 2 slides, I guess. You can analyze the model, or you can have some data and you want to do something with that. I will come to that in a minute. So what can be sources of uncertainty in your parameters? That can be natural fluctuations. Sometimes it's warmer, sometimes it's colder a little bit. You cannot control this particular well. That can be human-made fluctuations. We have seen these essays yesterday. They are produced. You prepare experiments, for instance, and there you have uncertainty in your system. You don't know exactly what you're doing. There can be lack of knowledge. For instance, you might not know how your source term really looks like. You might have an idea, but you might not be sure. And it can be lack of accuracy. You're giving the best to measure your quantities precisely, your parameters precisely, but there will always be measurement errors, for instance. So there are many sources where uncertainty can come in. And what do we assume now, and what is our objective? So a principal assumption, what I will make is, or what I will always come back to, that's not 100% necessary one, but a very convenient one. It's you have your model M and you have a black box solver for that. You just solve it. You don't want to care about the implementation. And in this particular implementation that you have, you can maybe even easily change the parameters and solve the model again and get your quantity of interest corresponding to modified parameters. Why do you want to use this black box solvers? Because normally you cannot afford to redo the implementation, to extend the implementation to do something else with your model. You have other tasks to do. And normally each model simulation is expensive, so you want, for what we want to do, you want to use as few model evaluations with your computer code as possible. And what you also need is, so that's sort of the computational side or the computational background for what I'm going to talk about. And what you also need is, well, some sort of information about the uncertainties in your parameters. You might argue, I'm happy if I know some values of my parameters. Now I'm supposed to also think about uncertainty in my parameters. Well, sometimes you have this available, in particular with measurement techniques. You often know that the true value is normally distributed around the measured value, and so on. So you can put that information into place here. And the objective of all what we're going to do is we want to gain additional insight into the dependence of the quantities of interest, U, from the parameters of the model. So we want to understand our model and potentially the process or the system it models better. And so now I'm coming a little bit to your question. There are two approaches, more or less. There's something called sensitivity analysis, and the other is uncertainty quantification. They are not, well, sometimes you cannot easily distinguish them, but I've tried here in the following. Sensitivity analysis is not dependent on the parameters which you have at hand. You have a model, there are parameters in there, but the sensitivity analysis does not depend on what you have actually measured, except for your parameters are maybe in a certain range or something. So, and what you want to do with a so-called local sensitivity analysis is you want to assess how my quantity of interest is changing as you change the parameters around a nominal value, around the typical value. And so you look at one value in parameter space and you see what's happening around that. How sensitive is my quantity of interest with respect to changes locally around this value? But you have a big parameter space, and you might pick a point in parameter space where you get some nice information, but this information does not hold at a different point in parameter space. And this is where global sensitivity analysis comes into play. And here the goal is you want to apportion the variation in your quantity of interest to each individual parameter. And you do this by considering all parameter combinations which you have in your admissible parameter space. So you really look at the full space, and you want to say this parameter is more important than that parameter for the quantity of interest I'm looking at. So and then you can use this for the identification of the most influential model parameters. And it is a model analysis technique. They do not depend on experimental data, except, well, in a very rough way. When it comes to uncertainty quantification, there you take the uncertainty which you have in your parameters as given. You have experimental data, and you have a model. You measure some parameter, and you have a model how uncertain or this parameter, this particular value is. And then you're asking, how does this parameter uncertainty propagate through the model, through your simulation, and changes the quantity of interest? And yeah, you want to obtain prediction intervals, the mean of your quantity of interest, standard deviation, possibly even a probability density function. And so this is, for instance, important if if you want to say the model what I'm using that meets some goals. If you develop some drug or some technique and you apply it, then you have to prove to the certification bodies that sort of your quantity of interest, what you want to achieve, is in a certain range, that it's not poisonous and so on, or below a certain threshold. And with uncertainty quantification, that can help you to get this measurements or this proof.
Question?
Yeah.
Are you going to do an example later? Because otherwise, oh.
Okay. Good. I want to do a little example on a tumor invasion model. It's based on one which Sandy Anderson and Mark Chaplin and myself proposed some time ago. So here we have three quantities in the model. It's very simple. And you have a tumor cell density C, you have an extracellular matrix density V, and you have a matrix degrading enzyme concentration M, which the matrix degrading enzyme M is produced by the tumor cells. That's this term here, plus alpha C. It degrades upon contact with the matrix, the extracellular matrix. The MDE can naturally decay, it diffuses in the domain, and what are our cells doing? Well, there's a random motility term here, so they move around a little bit, and there's a chemotaxis or haptotaxis term in this case, so they move up gradients of the extracellular matrix to invade, and there's a sort of logistic type growth term where we take sort of the available space as the limiting factor. And also for the chemotaxis, we have this factor here, which says if there is not enough space in the direction where you want to go to, then just stay where you are. So that prevents overcrowding, and we consider that in a small domain. It's all non-dimensionalized and so on, and with zero flux boundary conditions. And initially we have a lump of cells in the center of our domain. We have some sort of heterogeneous extracellular matrix density, and where the cells are, there's also some initial concentration of the matrix degrading enzyme. And as time evolves, these cells secrete matrix degrading enzyme. This diffuses in the domain, degrades a little bit the matrix here, and that makes room for invasion of the tumor cells, which also proliferate. So we'll have a look at this example later again. We have a couple of parameters here. There's some diffusion constants, sort of a proliferation rate, production rate, decay rates, and so on. We will look at these as parameters, and we will also look later on at the case that our parameter d1, that will be that might be space dependent. There might be spatial variations of the diffusion constant because, let's say, the extracellular matrix structure is changing around and in the domain, and this has an influence of the capability for the tumor cells to diffuse or to randomly move about. And but we don't know exactly how this spatial variation might look like. So we want to assess if there would be spatial variation, would that have a big impact on my simulation results? Okay. So we start with local sensitivity analysis, and this is there to compute or approximate the so-called local sensitivities. So we have nominal values p bar of each of the parameters, and the local sensitivity is just a derivative of u with respect to such a parameter evaluated at this nominal value. That tells you how much u changes if you change that parameter pi. So you have to differentiate this model M, and there are some basic techniques. There are finite difference approximations. We will see that. There's automatic differentiation, and you can use sort of sensitivity equations. We'll speak a little bit about this and the following, the first and the third point. Automatic differentiation just means there are computational tools which take your computer code and you say compute the derivative of my computer code M with respect to this parameter at this nominal parameter values in space, and then the computer program goes along and does this computation. That can be more or less efficient and more or less complicated, but sort of it's a sort of an automatic way of a more accurate way of doing finite difference approximations. Okay, for finite difference approximations, what we do is we simply approximate the derivative by difference quotient. Question or? No. Where we perturb our nominal value, or the ith parameter and the nominal parameter vector. So this is the ith unit vector. So we add a contribution delta I to pi bar. So this is our perturbed model, and we subtract the output of the non-perturbed model, and we divide by the perturbation, how big it was. And in order for this quotient to be an approximation of suitable accuracy, the choice of this delta I is important. And it must be in relation to the magnitude of the parameter. If it's too small with respect to the parameter, then on the computer this addition might end up to be might end up to be p bar simply, and you solve 2 times the same problem, and you get 0 dependence, which might not be true. It should also take into account the accuracy with which you approximate your model M. If your you have iterations, discretizations in your computer code, and if M is only determined up to a certain accuracy, it does not make sense to consider very, very small parameter changes, because then the effect of this parameter change will just be below the numerical noise, sort of, which comes from limited accuracy in evaluating M.
What if the model is fundamentally stochastic? I mean, so we do simulations where the difference in result for the same initial conditions can not only be a quantitative difference, it can be a qualitative difference. So we wind up with things like risk maps where you calculate the percentage of outcomes of a given time.
That is more difficult. It depends a bit on the dependence of your quantity of interest on the parameter. If your stochasticity has only a weak influence, then you can just go along. If it has a very strong influence, then you have to take that, of course, into account as well. But let's assume our model is deterministic. It's not good?
It wasn't clear on the last slide what you meant by automatic. You don't have to go back. Automatic differentiation. Some clever way of doing the derivative on the fly?
Yeah, it's sort of you write a function like you program it, for instance, in MATLAB, y equals x squared plus sine of x times x, and you call this function with a value for x. So this is your function f of y, y f of x, right? And you call then you call somewhere, I call it capital Y of f of x, and the capital Y adds a vector where you get f of x and f prime of x. And this is all done automatically. You're not doing anything yourself. This is all in the computer code, and they can deal with expressions like this. If it then involves loops and stuff, it's getting much more tricky, but there are codes for that. For instance, ADI4, it's for Fortran programs. You have tools for that in MATLAB, C, and so on. So you can invoke that, but it might be costly. And what it does, it computes this particular function value up to machine accuracy, sort of in the same accuracy as, well, up to machine, in the same accuracy as your f. Okay. Right. This approach to compute is computationally cheap. While to compute all these sensitivities, you just need n plus 1, n the number of your parameters, n plus 1 evaluations of n times the perturbed model and once the unperturbed. Okay, so if you go back to our model, what could be quantities of interest? I'm sure you can cook up much more interesting ones or much more appropriate ones. I've taken some fairly simple ones. You could be asking, what is the cell density at some point in time and space? For instance, your U could be the cell density at some point t star, x star, because that is particularly interesting for you. Or you may be asking, or you may be interested in the total cell mass at some fixed time point. So your U is the integral over your spatial domain of the cell density at time t star.
Sorry, one more question, and I know the answer. I sort of know the answer, but I think it's still worth asking. What if, I mean, this works very well if your parameters are scalars, but if your parameter, say, is the shape of the initial domain, then you have an arbitrary number of possible perturbations for the shape. At the very least, you have to do a partial derivative of.
I come to that later.
You'll do it, fine, okay.
Not in the context of sensitivity analysis, but I will do it in the context of UQ, but it applies here as well.
Well, that's why, because your initial condition could be an arbitrary pattern of cells.
For instance, yeah. Or at least, maybe you don't want to have it fully arbitrary, but in some sort of, yeah, some arbitrary condition, yeah, but not fully maybe. Yeah, but I come to that later on. And so here I've computed the sensitivities for when U is the total cell mass. So these are, well, normalized parameters. They have been chosen sensibly with respect to biology. And this is the nominal values which we've used. And then you can compute this finite difference quotient, and you get these sensitivities. And it appears that the D1 has a really, really big influence on the total cell mass. And yeah, you have to be careful here. If we go back, if you look at at our initial cell mass, there are regions of low and high cell density, and if around the tumor there's kind of a high cell density, so it cannot immediately invade, but and for chemotaxis we have sort of a barrier for that with this sort of fraction of free space term, which prevents them from just invading. But for the diffusion term we don't have this, so diffusively cells sneak through this into this regions where there's not a lot of extracellular matrix, and then immediately the cell proliferation kicks in. So that in fact tells you what you should do something about your model here, possibly. That explains the high sensitivity here, and you should not come first to the conclusion that this cell motility has such a big impact on the cell mass. So you have to be careful with these values. You always have to be careful when interpreting. Okay, for the well, the next biggest value that's sort of a little bit the same issue is this chemotactic sensitivity. And but then here, for instance, if you look at the growth rate, if you increase that, then you also get a fairly good increase in your quantity of interest, which is total cell mass here. On the other hand, for instance, if you increase lambda, that was the MDE decay rate, then you decrease the total cell mass because MDE degrades faster, so it cannot do its action as long as with the smaller value of lambda. So, and now you have to go back to your modeling assumption and try to make sense out of these values for your particular application and for the questions you want to address. Okay, so what we've done here is we have looked at some particular time point or time and space point. You might be interested in, if you have a time-dependent process, how does the sensitivity change with time and along your solution. And for that, we look at the initial value problem for an ordinary differential equation. U prime, your quantity of interest, is now the ODE solution. U prime of t equals f of t and u and your parameter values. And we have some initial condition, which may also depend on the parameter values. And what you're interested in is you want to have the sensitivities along the solution, so the partial derivative of u with respect to the parameters p. And we call this Si of t. And what you can do now, you can do this also with PDEs, is you differentiate your problem with respect to p, and you exchange the order of differentiation. Then you end up with a differential equation, ordinary differential equation for your sensitivities here with some initial conditions. And you can solve this in addition to your original problem. And then you compute, similar as with this automatic differentiation, you compute the solution of your ODE system together with the time-dependent sensitivities. And this system here has a particular structure. For instance, this Jacobian is, for each I, it is the same. And but the size of the dimension of this extended PDE system is n, also number of parameters, plus 1 times the dimension of u. If you have a big ODE system, that can be really big. Okay, but it can be solved using existing ODE codes. These codes become efficient if they're sensitivity aware, in the sense that they take this structure into account. An example is Linda Petzold's code DAS-PK, which has an extension for sensitivity equations, and you just get very efficiently your solution together with the sensitivities for, let's say, a moderate number of parameters. If your number of parameters becomes too big, then you get simply a too huge system, and you cannot, or you should not, or you don't want to do it that way anymore. Why do you want to have these sensitivities? You might want to fit data, calibrate your model, optimize in some sense. Then for your Newton type solver, you need sensitivities to get the search direction. So, and here you have a way of doing this with ODEs in sort of an integrated fashion. Yeah, you want to fit your solution, u of t, to some data. And this fitting would, yeah. Okay, what are the limitations of this simple approaches I've shown you? We always vary sort of one parameter. The simultaneous variation of more than one parameter, that's not possible. Variation of functional parameters, it can be done, but it's difficult. And in this example here, sensitivity equations, they lead to, say, a problem of the same kind from what you started. And so in that sense, you don't have to change your model implementation. You have to, well, beef it up a little bit, let's say. But if you do this in the case of PDEs, that can become really nasty. And that might change, you get a big PDE system now, you have to solve this, and that might completely change the type and structure of your PDE system, and you might have to think of a completely new and different solver to get solutions for this problem. So that's maybe not the way to go forward. There are advanced techniques which are working on a more functional analytic framework, and these are forward sensitivity analysis procedures or particular adjoint sensitivity analysis procedures. And this also becomes efficient for very large numbers of parameters because the problems you have to solve, they do not depend on the number of parameters anymore, but they depend on sort of on the complexity of your quantity of interest. Is this a scalar, a function, or something like this? So you can be much more efficient then. Okay. Like limitations of all those, also of the advanced techniques, is we consider variation only locally and we employ essentially a linearity assumption. And global sensitivity analysis will go beyond that because we consider the whole variation range of the parameters, and the parameters, they are now described as random variables that encapsulate somehow their uncertainty, and also it makes our quantity of interest a random variable. So it's, yeah. And the primary objectives of global sensitivity analysis include to identify and prioritize the most influential parameters, or sometimes equally important, to identify non-influential parameters because you can kick them out of your model. Right. So we're now changing our sort of model parameters a little bit. We've just said model parameters are given in terms of random variables. So for one model parameter, you might have 2 or 3 or 4 random variables which describe it. So our independent quantities are now n continuously distributed independent random variables. For the sake of understanding, you can just think of each random variable as an uncertain parameter, and that's okay. And they take, if you draw a random event, then they take values theta 1 to theta n. So n is now a number of random variables. It can be larger than the lowercase n, which we had as the number for parameters. And such a realization of the random variables is a vector, still in Rn. We're not talking about functions yet. And that's the element of, of the space subset gamma of Rn. And so now we write u, our quantity of interest, is m evaluated at y. And these n random variables, they increase the dimensionality of the problem I have. Before, when I started, without looking at uncertainties, I might have time and space dependent. Time dependent, 1 dimension, space 3, so I have a 4-dimensional problem, let's say. Now I have maybe 10 random variables which describe my problem. They live in this parameter space gamma, and I have to discretize this whole parameter space gamma, so I have a 14-dimensional problem, and that might be computationally quite expensive, and you have to think about that. Okay, what are typical distributions? They're all on finite intervals here. So the random variable could be uniformly distributed. That's the typical choice for design parameters. You want to, in the end, you want to, you can adjust some parameters in your process, and then you can sort of, with equal cost, let's say, pick any value in a particular interval. Often you have triangular distributions, so where the density function just looks like you have 3 values a, b, c, and then put it there, and yep, that's not a 0. And this is your density function. So it's just triangular shape. Or I guess what you have mostly with measured data is you have a truncated normal distribution. And all these distributions, they can be transformed such that you only sample each from the unit interval 0, 1. So you're in effect, your parameter space gamma can be considered as a high-dimensional unit cube. Okay, so if you want to do global sensitivity analysis, you can go along with 2 approaches, and the first one is a variance-based approach, so to compute so-called Sobol indices, And this approach is based, you're interested in the variance of your quantity of interest, and you do a decomposition, like a series expansion, of your variance into different terms. And these terms tell you something about the influence of each parameter or of certain parameter combinations on the quantity of interest. And with the help of these terms, you can rank parameters according to their importance, and you can quantify how much more important one parameter is over the other. And these terms in this decomposition, they're expected values. So you have to do many simulations to get a good statistics, and that makes this approach fairly expensive, in particular if your model M is expensive. We'll see later how we can reduce costs for models M. Right. Different approach, much simpler, so-called screening-based methods. We'll have a quick look at the so-called Morris screening. And what they do is, well, they compute local sensitivity approximations as before on a very coarse grid, and then they average those over the whole parameter space to obtain a global measure. And that's our global sensitivity index then. And they are based on a one factor at a time method, so we change one parameter at a time and compute those local sensitivity approximations. They also rank the parameters according to their importance, we will see. But the information which you get is coarse and rough, and it's not suitable to quantify the relative importance of one parameter over another, as with the more expensive method up here. But for that reason, they are also computationally less expensive. And what this Morris screening can do is it classifies our parameters into three sets, into three groups. There are parameters which have negligible effects. You might want to kick them out. There are parameters which have large linear effects and they do not depend on each other. So one change of one parameter does not affect how another parameter has influences the system. Or in the third case, we have large non-linear or interactions effects with other parameters. And I guess these are sort of the most interesting parameters in the model, because it's difficult to predict what they do. And the principal approach is you have your unit cube gamma, where your parameters or your random variables live. You partition each direction in L equispaced values. Let me do this for 2D. So say this is, let's call it parameter 1, parameter 2, and then so we have now a lattice, a 4x4 lattice in our parameter space. That's called gamma L, and so this is L equal to 4, and then we define, we don't call it local sensitivity, we call it elementary effect because it's very coarse. The elementary effect in some point y on this lattice in a direction I by a finite difference quotient. For instance, we can take delta equals 2/3, then we would have, and I equals 1, then we have this point and this point, 2 grid points to the right. Okay, and we compute these difference quotients for a number of, we can compute this for any q, which we have in the lattice, as long as the second, the q should be a y, sorry. That should be di of y. Okay, we can compute this for every y in the lattice, as long as y plus delta ei is also in the lattice. And then we compute statistics, and in order to cover the space later on, your parameter space nicely, this appears to be a good choice. And to get the statistics, we sample our elementary effects at R points for each parameter value I. So these are our sample points, and then we compute the statistics. We do not compute the mean because it might be positive, negative, and then contributions may cancel. So we compute the mean of the absolute values, but we compute the variance of the proper variance of these samples di of yij. And so what does it tell us? If mu I star is big, then the elementary then these elementary effects are big, and we have some effect. If mu I star is small, then we have hardly any dependence anywhere in our parameter domain, and we say parameter I has negligible effect. So mu I star small, we're in the first class for a parameter pi. If that is big, then we can look at the variance. If the variance is small, then this means that my d's are all close to the mean value. And this means wherever I am in parameter space, this difference is always the same. But this means you have a linear dependence of your model M on the ith parameter, and therefore we are in the second case. We have large linear effects without interaction, and if the sigma is large, sigma I squared is large, then this means we have strong nonlinear effects.
A question?
Yeah.
Would it be possible to generalize this to a situation in which the parameters may not be independent?
Yes, it is.
Yeah, possibly.
It is, but it's getting more complicated.
Yeah.
There are methods for that. Yeah.
Aren't you losing information here by taking the absolute value of those? Because in essence, you're saying that a negative change on the outcome is the same as a positive change.
Yes, the point is I might have a negative change in one region of parameter space and a positive change in another region of parameter space. And if I add them both, my mu tells me, it has no influence. But obviously, I can have a big influence here in one direction and a big influence there in the other direction. And this is avoided with this absolute value averaging.
Well, I understand that, but in your variance, you are doing it globally, right?
Well, but sort of I'm averaging here about positive constants.
No, I understand.
If you go, well, maybe we can discuss this later. If you go to statistics textbooks, they say it avoids type 2 errors or something like this in your estimating properties of your.
But it is much coarser than the Sobol analysis, right?
It is, yes.
Inflating the parameters in the Sobol analysis, you look at the variance introduced by one of the parameters with other of them fixed, right? You want to identify those parameters that contribute most to the variance. But here, it looks like everything is just getting mixed together.
Yeah, it's much coarser than Sobol, but it's in terms of simulation, it's more efficient. Well, it depends on how much fine-grained information you want to have. It's a cheaper approach to get some global information, but you're not getting as good information as with Sobol indices.
Well, in particular, are you able to identify parameters that contribute most to the variance?
Most?
To the variance. I mean, you're mixing all the variances together, right? So
Yeah.
and you identify particular parameters that are most important by this technique.
Well, you get the important parameters with the mu, which tells you something about the mu is tells you something. It's the mean of the variance of your variation in your quantity of interest.
We can talk later.
Yeah. Okay. So if you do a naive sampling here, you would need 2n times r model evaluations to get compute these quantities. With a so-called Morris sampling, you can reduce this to n+1 times R model evaluations, and you still cover nicely the whole space, your parameter space, if R is like the number of your repetitions is big enough. Okay, I have an example here. What you get from a different example, that's a multi-scale model of the elastic stiffness of some tendon, which we had looked at, and what you get is for each parameter, the parameters are not that much important here, you get a mu star value and a sigma value, and can plot them in a diagram like this, and then you have a region where mu star is small, say this, and you classify these parameters as unimportant because there's not much, they do not contribute much to the variation of your quantity of interest. And then you have those, say, below the diagonal, where your where the oh, here's a square missing. The sigma squared is small compared to the mean value mu star, and this is where you expect linear interactions. And for instance, with this parameter, this is sort of driving parameter for the problem here. And but you also have parameters appearing in this where you expect nonlinear dependence on the parameter, and that's a distribution parameter where mineralization in the tendon takes place. And not much is known about it. It's known that such a distribution exists, but not much is known about how this really looks like. But it appears from our analysis that we really should look at this parameter also experimentally. So this is what we've learned in particular from this study. Okay, right, that much maybe for uncertainty quantification and for sensitivity analysis. And now we want to go to uncertainty quantification. What we do there is we model the uncertainty, or the typical approach is we model the uncertainty in parameters pi by random variables or random fields. And this now comes to spatial dependent parameters. And so you have some data, and you can represent them by this. You're in the situation, before you were asking, okay, what parameter is important, more important, what is less important. Now you're in the situation, okay, you have a parameter with uncertainty, you cannot do anything about it. You have to, or you want to live with that uncertainty. What effect does it have on your outcome? Right, so here goes sort of your data in, if you like, in this modeling step. And then you define the quantities of interest depending on the question which you want to address. That's, I guess, a very important point. You sample parameters and compute corresponding quantities of interest. And then you compute statistics, mean, variance, density functions, and so on. And from these computed quantities of interest. And so this looks very much like a Monte Carlo approach. And if your parameter space is big, then that might become very expensive. And as before, we assume that we have a black box solver, M at hand, which we want to use. And we do not assume we have just random fields going wild, but we have correlated random fields, and we'll see one later in the talk. Or is it on the oh, yeah, there it comes already. So we have correlated random fields, and we can see this here. We go back to our tumor invasion model, and before we have used our diffusion coefficient, random motility coefficient of the cells, simply as this scalar value, and this is what we consider. So, but yeah.
Give me an example how such a correlated uncertainty field might arise.
Well, if here's an example, and I'll say something to this. Okay. So here we see, and we perturb this fixed value with with a random variable. It's a Gaussian random field here, and this is the difference. So you see the difference to the nominal value is changing rather smoothly. And for instance, you might have some gradient in your, or a non-homogeneity in your extracellular matrix. Yeah, you have where is it? So that's positive. So here and here you have a higher extracellular matrix density, and therefore, for some reasons, that leads to interactions, and the cells are not as motile as in regions where there is less extracellular matrix. What we not want to look at is the cell random motility jumps up and down from one place to the next. Then we cannot do anything with our approach. We need sort of a slowly, more or less slowly changing parameter, but we don't know whether it stands here or stands there. So that can change. That's one realization. A typical, probably a typical realization. We can draw another random event. We get another one where the peaks are elsewhere. We don't know where, but what we assume, or what the modeler tells us, they sort of change in a nice way, let's say, or the experimentalist says that, or whatever. Yeah. Okay, and then we can compute our cell invasion model, and this is now the solution at time t equals 60, or t after 60 time units, and that's a unit square, so the whole domain is a little bit bigger, so that you can see it better. I've zoomed in a little bit, and the tumor has invaded. It was only very concentrated here in the middle in the beginning, and we see that the heterogeneous matrix led to some heterogeneity on the tumor extracellular matrix interface, which we plot here a contour at 10 to the minus 2 tumor cell density. This is this ring which you can see, and then we can take this random motility coefficient, and we get something which sort of looks similar. But if we look at the difference, we see it was invading less here when in the other direction, and this is because, so let me, this is d1 minus, because this is negative. Yeah, because we have a smaller diffusion coefficient here. I guess I mixed up high and low cell density, which can lead to this. But we have a smaller random motility coefficient in that region, and therefore cells do not invade as fast into that region, and we get a shift of our solution more towards the right. So it has some effect, and I have some very coarse measures. We just take the relative error, take the relative difference of these solutions in the whole domain, and then we take the 2 norm or the infinity norm of that, and this is our quantity of interest. We want to see how much does the result change if we go from a fixed diffusion coefficient to a sort of modulated diffusion coefficient. How much impact has the possible spatial variation on our results? And maybe a more refined measure would be sort of asking about the roughness of the interface or things like this, but we have not done this here.
So in your upper right-hand diagram, was there a correlation between the diffusion and the cell density?
In this diagram?
Yeah, what does that represent?
Well, this is sort of, we postulate that the diffusion coefficient is not a constant in space, but varies around, sort of, let's say, around the mean value.
Yeah, but then why does it turn out that in a region of high density they diffuse less?
No, I said I mixed it up. So in this region, you have a lower. Well, I was talking about matrix density, which could lead to that. Not cell density.
Are those correlated? Are those correlated in that? I understood that to be a constant plus noise.
Well, all I'm saying is the noise is, or all I want to say is the noise is just not like white noise, where you get a highly oscillatory behavior, but you have correlation in your random field, and that leads to a sort of a smooth variation of your diffusion coefficient around its mean value.
How does that enter into the Gaussian?
Sorry?
How does it? You say that psi is a Gaussian random field.
Yeah.
So how does that dependence on the matrix density enter?
There's it's an example, and I don't have any dependence on the matrix density. I just said if you go to biology, there might be changes in local matrix density, and they might impact on the ability of cells to move about randomly, and possibly that could be a model of that, without going into much physics. So there could be an effect, and the question is that effect significant? Will that be the result of my analysis? Then I should go to the lab and make sure I can measure that. Or the outcome of my analysis is, if you have sort of variations like this, then that will not impact much on the results I obtain from my model, and I just don't have to care about if there's a spatial variation. In future simulation, I will neglect it as long as my other conditions sort of are still supporting the analysis as I did here, and I can solve the simpler model with a constant diffusion coefficient.
And this is for one realization, so you have to run many realizations.
This is exactly the point. This is for one realization. Now I can throw the dice again, a different omega. I get a different sort of perturbation of my nominal value. I get a different shape here. I get a different difference. I get a different value of the quantity of interest. And then I want to consider sort of all realizations of my random field. And I want to have the answer. This variation in there is important to that extent, or I can learn it's not important and I can forget about it again. Right, there are two computational challenges at this point. I have this infinite dimensional random field, and I somehow have to approximate it, and a tool for that is, for instance, the Cohen-Loewe expansion. I will very, very briefly or quickly, let's say, go over this in the interest of time. And then I have to find suitable and efficient sampling from a high-dimensional space, because each sample means solve this problem, and I can't afford too many of them. Okay, and these challenges computationally, they're on top of a possibly challenging model. Okay, right, that's maybe a little bit technical. Cohen-Loewe expansion for a random field psi, and we assume we have existing first and second moments, and the expected value E of psi and the covariance function, they are known. So that's what, if I sit together with an experimentalist, that's what we would have to come up for such a random field. These, in particular, this covariance function in computational geophysics. For instance, there are lots of covariance functions have been used, and so there's quite some source of where we could draw from. And this covariance function should be continuous, and then you can write down an eigenvalue problem with this covariance function over your spatial domain D, and this has non-negative eigenvalues and corresponding continuous normalized eigenfunctions Fn, so lambda 1, 2, 3, and F1, F2, F3, and they form a basis of the orthonormal basis of the L2 space. And the Calhoun-Loewe expansion now says you can write your random field as the expected value plus an infinite sum, where you have a random variable, theta n, and then you have a deterministic part, square root of your eigenvalue times the deterministic eigenfunction. And the psi n, there are random variables like this. Well, essentially we don't know them. That's still a problem, we come back to that. But you know they are centered, they are mutually uncorrelated, and they have unit variance. That's what you can show. Well, now you can go along and say, well, I'm not adding up these terms up to infinity, I only add up to capital N. And then I have capital N random variables here, as we had in our model. And we have a finite sum here. We can compute eigenvalues, eigenfunctions, so this can be evaluated. And you can also show what's the error which I make when I cut off my series at n. It's just the sum of the remaining eigenvalues. And the decrease of the eigenvalues depends on the regularity of your correlation function. And you normally fix n such that 95% of the eigenvalues are contained. Well, you try to fix n that 95% of the information is maintained. So you look at the sum of the eigenvalues which you have, you compute some more and see if this changes significantly. And make some estimates. Good. If you have a Gaussian random field, then the important point is that these theta n random variables, they are again normally distributed. For Gaussian random field, you know the distribution of the thetas. For other random fields, you don't know this. So what you then pick for theta, which distribution, becomes part of the modeling. And they also, for the theta, they also form a basis of the stochastic space. And so in some sense, you have now a correspondence between your random field psi and the random variable theta n. Given that psi, you have all these theta n, or otherwise, you pick some theta n values, draw normally distributed random variables, and form this sum, and you get the psi back. So, and that makes it easy now to sample from your random field. You just draw capital N normally distributed random variables, and you form the truncated Calhoun-Loewe expansion. And you can compute the eigenvalues and eigenfunctions with a Galerkin projection. That's maybe not so much of interest here. You can use particular methods. And if you do this for our random motility coefficient, where psi is now a centered Gaussian with expected value 0, that's what this means, and with unit variance, then we use a squared exponential covariance function here, which is frequently used and gives you rather smooth results. Then I've plotted you here the largest 150 out of 1,600 eigenvalues which I've approximated. So I've computed 1,600 eigenvalues of this covariance function, and these are the largest 150, and they sort of go from 1 down to 10 to the minus 15, and all of us are even smaller because we compute the largest first. And you require only 6 of them to capture 95% of the information, roughly. So we approximate our random field here with a series of length 6. So this gives us a 6-dimensional parameter space, which we have to use for uncertainty quantification. And there are more options for the covariance function. And if positivity of a parameter is critical, you can use so-called log-normal random fields, and you don't get negative values in sampling, which might be convenient for some parameters, I guess. Okay, so we have parameterized the random fields in the model through finitely many random variables. we have used truncated Karl-Löwe expansion. You can do also polynomial chaos expansion. There are a couple of other options. And the model parameters, as before, are now a finite dimensional vector of random variables. So we've transformed our infinite dimensional problem back to a finite dimensional one. And as before, M is now still deterministic, but high dimensional. And we can use this parameterization of random fields also in the local sensitivity methods I've shown before. Okay, so what are we doing now for uncertainty quantification? We use the so-called stochastic collocation approach. And in essence, that provides us with an interpolation function from our parameter space gamma, which we sample at some collocation points yj, and this interpolation goes from parameter space gamma to the quantities of interest u. So we construct a function somehow, and it should be cheap to evaluate. That function should sort of represent somehow the model nicely, and it should be cheap to evaluate because then we can cheaply compute statistics of u over gamma, mean values, variance, probability density function, whatever we like. And what we do is we select collocation points. I will say something about this in a minute in our parameter space gamma. Then we solve, hopefully in parallel, the deterministic model for all new collocation points which we've just selected. We'll select more down here, that's why I wrote new here. Then we construct the collocation polynomial that interpolates u in all these collocation points. So we put the function through the data points which we have. We compute an error indicator which tells us we have met a tolerance goal, then we are done, or we have not met the tolerance goal, then we adaptively add collocation points to those which we already have, and we go to step 2. And once this algorithm terminates, we compute statistics. Okay, so what collocation points can we use? We could use, like in a Monte Carlo fashion, we just draw random points, but that could be too many. And we have a smooth more or less smooth dependence between the parameters and or we assume a rather smooth dependence between parameters and quantities of interest. So we should be able to make use of this, and for that reason, we use structured and sparse grid. So structured leads to computable collocation points in a particular fashion, and sparse means we avoid, as compared to full grids, the curse of dimensionality, and the sparse grids are constructed using Smoljac's algorithm. And the grids which we construct, if we one set of, or the set of collocation points, if we have one set of collocation points and decide we need more, then we nest them. So we can reuse all the simulations what we've had before to get a better interpolation function. We also use anisotropic grids, and they allow for dimension adaptive refinement, so we can refine more along the direction of one parameter, because that parameter might have a stronger influence, as compared to into the direction of another parameter. That also saves, again, on model evaluations. And we choose our collocation points such that we can easily evaluate the moments of u, and if we easily evaluate moments of u, we have the mean, the variance, easily available, even in sort of analytical form here. So let's have a look at these grids and the difference between full and sparse grids. So these are sort of the steps, the grid points which we can add to go on from a very coarse grid here. We add in this direction or in this direction and get finer and finer grids. You will see that in a moment. So that's the cheapest, and this is for 2 parameters again here. So you can do the same in any number of dimensions. So that's full and isotropic, same in each direction. And if we take these 4, then this is again a full grid, isotropic. We do this, and we do this, and if you imagine this in 6 dimensions, and you want to do this another 2 times, then your computing people are coming and say, well, you can go on holiday, and then afterwards we might present you with some results. That will not work in most cases. So here we consider a sparse and isotropic grid. So now we don't go in squares along this pattern on the left, but we only add a diagonal. And of course, if you go on and on, you also get all the grid points, but you do it in a much more gradual fashion. Yeah, you have more grid points, like here on the boundary, but these ones here in the middle, they are still missing. So that gives you quite a reduction on your number of grid points. And you can have a full and anisotropic grid, then you go sort of in rectangles. You always have a rectangle on in this rectangular pattern on the left. Or you can say, well, this direction here, this is more important when this direction down, and so you have more grid points in this direction when in the other one. So that's sparse and anisotropic. And we use Lagrange interpolation on these grids. With a nodal basis, all the basis functions change. If the number of collocation points is increased, that's not nice because we always have to recompute. Therefore, we use a hierarchical basis. And this also gives you sort of error indicators. You have an interpolation polynomial, and you add some collocation points, and you get additional terms for these new collocation points, but the rest is not changing. And this means that you can quantify what the addition of the last collocation points meant to your interpolation function. Was this a big contribution? Then you possibly should refine further. Was it a very small contribution below your tolerance level? Then you might stop and say, I think I'm accurate enough. So it's an error indicator. It's not an error estimator. If you want to make it an estimator, you have to do some heavy analysis. You can do this in some cases, not in all. And I've not seen it for stochastic systems anywhere. And the global interpolation, that can be replaced by local interpolation, for instance, piecewise linear interpolation. There's a nice paper by Ma and Savaras from 2009 introducing this with some computations. Okay. Good. Higher moments. Yeah, once we have this interpolation, we can use now we can cheaply use a Monte Carlo scheme because we just evaluate the polynomial very efficiently. And we can compute all the moments or statistics which we want using Monte Carlo. We have also selected collocation points in a particular way to give good quadrature rules, and for certain distributions we can now evaluate the moments more or less analytically very fast, and that gives some additional advantage here. And for the tumor invasion model, what is the uncertainty quantification saying? So, well, that could be a bit boring for you. It's just numbers. No fancy pictures here. The input has stochastic dimension 6. We have discretized our random field with 6 random variables and according deterministic function. Requested a tolerance of 10 to the minus 2 in our UQ, and the required collocation points or in simulations ended up to be 309. That's not a few, but it's also not in the order of 1,000, 2,000, 5,000, 10,000. So, which you might have needed with Monte Carlo, simple Monte Carlo. And the output is we give you the expected value and the variance for the 2 different norms of the relative difference. And yeah, it's rather small, and does this now mean for you as an experimentalist, as a modeler, we have to go into this parameter with more detail or not? That's what I guess needs to be discussed. And as I said, the quantities of interest I've chosen them rather ad hoc, and so there might be more interesting ones. Right, we can compare the stochastic collocation approach with some other approaches. It is a non-intrusive method in the sense that the deterministic model remains unchanged. We just solve it for different values of parameters y. So Monte Carlo is and its variants are also non-intrusive methods. They are simpler in their implementation. The drawback, well, the quasi-Monte Carlo methods maybe not, but the drawback is the low rate of convergence. With stochastic collocation, well, the sparse grid is sort of fairly simple. I mean, you have routines for that, and as a practitioner, you don't have to care too much about that. And rate of conversion goes up for smoother U, and it's the number of simulations you need is mildly dependent on n. And you can, we have done simulations with up to 20, 25 stochastic dimensions, and that's then already quite some effort, but still doable. With many more, it also becomes expensive. Yeah, intrusive methods, you might have heard stochastic finite elements, also very nice. You expand your solution U or your quantity of interest in terms of polynomials with deterministic coefficients, and the result is, as in the ODE case, which we've seen in the local analysis earlier, a high-dimensional coupled deterministic problem. And how to solve this efficiently is not always clear. Completely new problems might arise, and so often this goes along with much more preparation when a stochastic collocation approach, which is sort of a little bit more ad hoc, but gives you results more quickly. Good. Sensitivity analysis and UQ uncertainty quantification may give additional insight into mathematical models. There exist algorithm software that can make use of black box implementations. That was a little bit the focus here. And often they can make immediate use of parallel computational resources, which is also nice. What are you as a modeler asked to provide or contribute to? Which output quantities are of interest to answer the research question? I guess that's the most important point to start with. Which parameters in the model are subject of uncertainty? And this is probably the most tricky point in the end. How can this uncertainty be modeled? And I'm not saying you have to do this all the time, but I think it's nice to know that methods like this are available, and if you see the need arising in your work, then you should approach some mathematician numerical analysis, and they can help you further. And yeah, I was looking at Darcy Thompson on growth and form, and on the back page of the title page, so page 3 or something, he quoted Stephen Hale from 1722. The reasoning about the wonderful and intricate operations of nature are so full of uncertainty that, as Weismann truly observes, hardly do we guess right at the things that are upon earth, and with labor do we find the things that are before us. So even in 1700 they were thinking about uncertainty, and well, there's a connection to Cambridge. Darcy Thompson published with Cambridge University Press in 1917. Then was a revised version, a second version, and it was just republished in 2014, I've learned yesterday. So thank you very much.
There are a few additional questions.
You talked about, that was very nice to show how you could expand potentially infinite dimensional fields in a manageable way. There's the reverse problem shows up, and maybe that comes under your stochastic collocation in the example that David gave the other day, which is, suppose you have a set of n chemical components, and you imagine that the topology of the reaction network is a variable. So you want to consider all possible topologies. Now, you could consider that as essentially 3 to the n, where you have a plus, minus, or no link between each component, and then you have parameter variations on the links which exist. Or you could just say that you have a continuous variable, which is everything links to everything else with a continuous value. Now, of course, the problem with that is that you then have an extremely high dimensional space to examine. And I just wondered if that you have any thoughts about how the question of dealing with discrete parameters, where a parameter is restricted to, say, 0 or 1 or plus or minus 1 versus continuum interpolations of those parameters.
We have not considered that. I know of some people, they look at robustness of production processes and look at uncertainty there, and they want to cut metal sheets and stuff, and there they also have discrete decision variables.
Right.
And there is work, but I cannot precisely tell you.
So
Like uncertainty quantification, I think in the engineering community, it's a long established thing, and people do this sort of with different methods all over the place, because they have to provide evidence that their construction are within certain limits, for instance. Yeah, they might not always call it uncertainty quantification, but in engineering it's very much established, and I imagine that even there you can find algorithm. But I could also point you to some colleagues doing this stuff.
Any other questions? Okay, let's thank Alf again.